Hello dear students, hope you're doing well. So this week we'll have chapter 3 starting from section 1. In section 1 there isn't a lot to explain, there's just memorizing stuff. We have qualitative properties of some gases, meaning how do they appear to us, some of their properties such as one of the smallest or one of the easiest example is color, solubility in water. So number 1 is color, number 2 solubility in water, when it dissolves in water, whether it has high solubility. If it has high solubility, meaning it dissolves fast. If it has low solubility, it means it either does not dissolve or only a small portion of it dissolves. Number 3, effect on the glowing splint, what will happen to it. Sometimes nothing happens to it, other times it lights up. In special occasions, special conditions, it might explode. It depends on the nature of the gas. And the last one is with litmus paper. Litmus paper, as it is shown in this figure 3.1. This is the litmus paper. We can use it to identify or to distinguish let's say gases or other substances such as acids and bases. You'll take this in later chapters as well, but you know that we can use it to identify something. Let's have a look at this table, in which you should memorize it because you get a lot of bubble sheet questions on this, and later in the basic question we'll have the same table, we'll just fill it in. Starting from the color NO2, nitrogen dioxide, it has a reddish to brown color. For Cl2, it is yellow to green. So for O2, as you know, it's colorless. Same thing goes for hydrogen, nitrogen monoxide, ammonia, and hydrochloric acid. All of them are colorless. So the only two colors that you should memorize is for NO2, which is reddish brown, and for Cl2 is yellow green. All the other ones, all of them are colorless. In order to memorize, you have to find tricks. Number 2, solubility in water. We have 3 of them with high solubility, and the other ones, all of them are low soluble. So the high solubility one is number 1, nitrogen monoxide, ammonia, and hydrochloric acid. The other ones, all of them have low solubility, meaning they either do not dissolve or you have to change the conditions in order for them to dissolve. Effect on the glowing splint, we only have 3 in which you have to memorize. O2, the splint relights, so it lights up. Hydrogen, which is a highly reactive gas, explosion happens. For nitrogen monoxide, the gas becomes brown in air. With the exposure of air, it becomes brown. The other ones, no effect, nothing happens. The last one for litmus paper, for nitrogen dioxide, it's red, so the litmus paper is changed into red, okay? For chlorine gas, it is bleached into white. For O2, nothing. Hydrogen, nothing. For nitrogen monoxide, NO, it turns red in air due to the presence of NO2. So NO changes into NO2, then it changes the litmus paper into red. Okay, and for ammonia, it's blue. For hydrochloric acid, it's red. This was it for this table. Let's go to the basic question and we're done for this section. So basic question, let's solve it. Try to solve it after you memorize it. Let's solve it. So NO2, first let's start with the color. The color of NO2, which is reddish brown. For chlorine, yellow to green. And the rest, all of them are colorless. Let's go to solubility in water. We said only 3 of them have high solubility, which is the first one, NO2, high, and the last 2, which was ammonia and hydrochloric acid. So we have ammonia high, The rest are low solubility. The action on the glowing splint. Nitrogen dioxide, nothing. Cl2, nothing. O2, it relights the splint. For the highly reactive gas, hydrogen explosion. For ammonia, nothing. The effect on the wet litmus paper. For NO2, it's red. For Cl2, bleached. O2, nothing. Hydrogen, nothing. Ammonia, blue. Chapter 3, Section 2 will talk about the quantitative behaviors of gases. So we will deal with numbers. Section 1, we have the relationship between pressure and volume. If let's say we have this container, if we let's say decrease the volume, know something that the relationship between pressure and volume, they are inversely proportional to each other. What does that mean? Meaning if you increase pressure, volume will be decreased. If you decrease pressure, volume will be increased. So inversely proportional. So in this case, if let's say we have this container filled with gases, whenever we're talking about pressure, we only talk about gases. We only mention gases because solids and liquids, nothing happens to them when you increase the pressure. So it's only related to gases. So we decrease the volume, let's say to half. Okay, this was the whole thing. We decrease it into only this. So let's say half. Okay, so what will happen to the pressure? More than we are decreasing this, the volume, what will happen to pressure? It should increase. Why does this happen? Because we are decreasing the pressure, so there is less space between the particles of gases. So what happens to them? Know something that gases, they are in constant movement, so they move a lot. When they move, they hit each other and the walls of the container. So because they have less space to travel in, it means that they will move faster. So moving faster, they will hit themselves and the container walls faster, meaning that the pressure will be increased. So scientists, they did an experiment. Let's say they took hydrogen chloride, so HCl gas, and ammonia, NH3, and these were the results of the experiment. So they changed the pressure from 1, then to 0.5, then to 0.1, so they decreased it. And they saw something amazing, in which whenever you do that, whenever we change the pressure or change the volume and keeping the other one constant. So in this case, you change the pressure, and so what will happen to the volume? So you cannot change both of them at once. And they saw no matter how much was the mass of each substance, for example, HCl was this much, ammonia was this much the mass. The ratios, the numbers were the same thing. So whenever you multiply P times V, you always get a constant, a number. So it doesn't matter how much was the mass of each substance, they got the same number. When you change the pressure, they got the same volume. What does this mean? Well, later we'll talk about it more. So let's talk about the law of combining volumes of gases, or to be specific, the Gay-Lussac law. It says that when gases react together to form new substances, they always do in the ratios of whole small numbers. What does that mean? Meaning you should have a whole number, not decimals, not fractions. For example, you cannot say 0.33 molecules of oxygen, they react with 1 molecule of hydrogen to produce 0.333 molecules of H2O. Okay, we have them as whole numbers, only whole numbers, not decimals. So from 1 to etc. And small whole numbers. Let's take 2 examples, for example, or 3 examples. This table, If, let's say, hydrogen reacts with chlorine to produce hydrogen chloride, which is HCl. Let's write down the equation. So 1 volume of hydrogen, in nature hydrogen is H2. It reacts with, so plus chlorine 1 volume, Cl2, to produce 2 volumes of HCl. Okay, the second one, we have 2 volumes of hydrogen. Look, 2 volumes of hydrogen. It reacts with 1 volume of oxygen to produce 2 volumes of steam, of water vapor. The last one, 3 volumes of hydrogen, reacts with 1 volume of nitrogen to produce 2 volumes of NH3. If you look at all of them are small whole numbers. We do not have decimals, they should be small whole numbers. Just imagine them as, let's say, blocks. In order to build something, you do not need half of something, there are a fraction of this block. You need it as whole numbers in order to build, let's say, a wall, for example. Next, we have Avogadro's hypothesis. Avogadro, he suggested that at the same temperature and pressure, meaning temperature and pressure, if they're constant, okay, equal volumes of different gases contain the same number of particles. What does that mean? It means if the conditions, the temperature and pressure, if they're constant, let's say temperature is 0 Celsius and pressure is 1 atmospheric pressure. For both of them, both containers, these are the conditions. Each container has its own gas, so gas 1, gas 2. Because they're under the same conditions of temperature and pressure, we should have the same number of particles here. If, let's say, we have 2 particles here, we should have 2 particles here as well. Okay, so this is what he suggested, what Avogadro said about gases, which later on you'll see that it might not be 100% true. Next, we have Dalton's atomic theory. Dalton, he talked about atoms, the structure of atoms, talked about elements, compounds, and so on. So we have points, we have to know them. Number 1 is that he says that the simplest substances found in nature, we call them elements. Okay, as you know, in the periodic table, we have more than 100 elements. So each square consists of an element. We already know this. So each element, they consist of tiny particles. What do you call them? We call them atoms. Let's say we have oxygen. Okay, this oxygen, it has many atoms. Okay, if you look closer, you should see atoms. But all of these are identical, meaning for oxygen, all of them are atoms of oxygen. Let's say for hydrogen, all of them are atoms of hydrogen, identical. And the hydrogen and oxygen, they do not have the same type of atoms. We cannot see for oxygen, let's say we have atoms of oxygen and some hydrogen with it. No, it's all of them should be atoms for oxygen. Same thing goes for hydrogen, all of them should be atoms of hydrogen. So that's number 2. Atoms of one element, they're all identical. They are different in properties and masses from other atoms. Each one of them, for oxygen, has their own properties, has their own mass. For hydrogen, again, has their own properties, has their own mass. Number 3, when elements, they combine, they form compounds. Okay, let's say hydrogen combines with oxygen, one atom of oxygen. When it is bonded to 2 atoms of hydrogen, it gives us a compound. This is water, H2O. Okay, so different elements, it means we have a compound. Same type of atom, it means we have elements. This is a compound. Let's say we have a glass of water. We have many molecules of water in this glass of water. But for element, we have many atoms. So the smallest particle for an element, if you look closer, you see atoms. For compounds, if you look closer, what would you see? Molecules. You took this in grade 9, I think. We cannot say, let's say, elements, they have molecules, but if in nature oxygen, it's O2, look, meaning it's oxygen bonded to another oxygen. Oh, this is a molecule. Okay, but if it is alone, it consists of atoms. Number 4, and the last one, atoms cannot be created or destroyed. You cannot create atoms from nothing, and you cannot destroy it into being nothing. They are conserved, just like here. Your chemical reaction should be balanced. Later we talk about how to balance chemical reactions. They should be balanced, meaning, let's say hydrogen reacts with oxygen to form water, right? So we have hydrogen reacts with oxygen to form water. How does this happen? It only happens when, okay, when two molecules of hydrogen reacts with one molecule of oxygen to produce two molecules of water. This is how it would be balanced. This is how number of atoms are conserved. But if I say hydrogen reacts with oxygen to give H2 water, look, here we have two hydrogens, two, correct. Oxygen, here we have two, on your right we have one. So this cannot happen. What about the other one? It cannot just disappear. No, it does not happen. That's why we balance it. We change these numbers right beside them, number of molecules. Later you'll talk about the steps on how to balance chemical reactions. But know that you cannot create them, the atoms, and you cannot destroy them. They are always conserved. This was about Dalton's atomic theory, his points. Okay, let's talk about how to write chemical equations. Look, things react with each other to form products. So we have reactants on your left, then you have your arrow, then you have your products on your right. You could have two reactants forming one product. You could have one reactant forming two products. It depends. For example, here, carbon reacts or combines with oxygen to form, so you have the arrow, to give, to produce, they're the same thing, the product. Okay, so here, where are the reactants, where are the products? Carbon and oxygen, both of them are reactants. On your right, this is your product. So look, we have two reactants and we have only one product, and it is okay. And look at the number of atoms. We have one carbon, one oxygen, which is correct. So later on, the thing that Avogadro said, we talked about it, and Dalton's points, we talked about them. Dalton rejected Avogadro's hypothesis. What did Avogadro mention that he rejected? Monet, he mentioned that at the same conditions, two different samples of gases, they have the same particles. Why? He said because they're under the same conditions, so they should be identical. But Dalton, he said no. He rejected his hypothesis. If they're under the same conditions, they have the same number of particles, this should happen. So one hydrogen should react with one oxygen to form water, H2O, which is not correct, right? We talked about this. It's not balanced because the number of particles, number of atoms of elements, they should be equal. They should be conserved. You cannot just destroy them into nothing. So the real thing is that two volumes or two molecules of hydrogen should react with one of oxygen to produce two of water vapor. And this is it. And this is proven experimentally. If you do the experiment, you'll see that two molecules or two volumes of hydrogen reacts with one of oxygen to form two volumes of water, which in which this rejects Avogadro's hypothesis. So this is incorrect. When he said equal volumes of gases, can they have the same number of particles under the same conditions? No. So the real thing is equal volumes of gases cannot have equal number of particles under the same conditions of temperature and pressure. So Avogadro is wrong. So what do you think? Will Avogadro just say, okay, you have proven me wrong, and say nothing? I don't think so. So what did he do? He responded. So he was trying to prove himself right. What did he say? He mentioned something in which no one talked about it, that in nature, gases, especially hydrogen, oxygen, in nature they are diatomic. What does that mean? Meaning we have two atoms. So in nature, oxygen is not just O. No, it's O2. In nature, hydrogen is not hydrogen alone, one atom, monoatomic. No, it's diatomic. So two atoms, they're bonded together. That's why his hypothesis was proven to be wrong. So he tried to defend himself by saying this, which was later on appreciated because it was a big deal in their experiments. So they are diatomic in nature. If you consider this, then his results or his hypothesis would agree with the experimental facts that they have got. Later, Dalton, he responded again. He tried to cover it all up. He responded with two questions. Avogadro, he couldn't answer. Later on, they answered it. So number one, why should two atoms of the same element combine to form a molecule? So why should hydrogen, let's say, combine with another hydrogen to form a molecule of hydrogen? Why not hydrogen and another oxygen? Okay, later on we'll talk about this. Then the second question is why should two atoms of hydrogen react with one atom of oxygen? Why should one oxygen come and form two bonds with hydrogen to form water? Why not, let's say, two oxygens bonded to one hydrogen? Something should be behind this, right? Later on, we'll talk about their valence electrons, something to do with their valence electrons. Depending on that, you'll know how many bonds they should make or they can make. For example, hydrogen has only one valence electron, so it is only able to form one bond, not two bonds. Oxygen, it needs two, so it should react with two things. It should be bonded with two things, not one. So this was proven when, after 50 years of Avogadro's death. So he was not able to see it with his own eyes, but he has contributed something huge by saying that they're diatomic in nature. It was a big deal. The last thing we have for this section, it is atomicity. What do you mean by atomicity? You just count the number of atoms in a molecule. For example, we have H2O. Look, the small number in between them, this belongs to hydrogen. If nothing is here, meaning it is 1. So how many hydrogens do we have? 2. How many oxygen? 1. Atomicity, you just add them. So 2 plus 1, 3. Let's do another example. NH3. Nothing is here, so it's 1 nitrogen plus 3 hydrogen, which is 4. This is atomicity. If, for example, we have NH4OH and we have a 5 here, ignore this big number. You only count the subscripts, the small numbers. Again, nothing here, so 1, that's 1, plus 4 here, that's 4. Look, O and H, there are two different elements, so 1 here, plus 1, and H here, plus 1. So the atomicity is 7. This is atomicity. You just count the number of atoms, the small numbers, not the big numbers. Ignore them. The very last thing we have for this section is basic question number 2. Look, for A, explain the letters and digits. What do they mean in this expression? Look, we have this big number, the big number here right beside your compound. It's the number of molecules. So you have 3 molecules of this. It means that if you have glass filled with this substance, we have 3 molecules. So H2SO4, that's 1. Another H2SO4, that's 2. Another H2SO4, that's 3. Okay, so number of molecules. These letters, as you know, H is hydrogen, S is sulfur, O is oxygen. Numbers, subscripts. This belongs to hydrogen, so 2 atoms of hydrogen. Nothing here, so 1 atom of sulfur. 4 here, so 4 atoms of oxygen. All of them, they're bonded together into giving H2SO4. B, explain this equation in words. Describe it. So 2 molecules of hydrogen plus, meaning it reacts with, so it reacts with 1 molecule of oxygen. The arrow meaning to produce, to give, to form 2 molecules of water. C, what is the atomicity of the following? Ne, it's neon. Look, one of them is the uppercase letter, another one is lowercase. So it means that this is only one element. Nothing, we do not have any numbers, so atomicity is 1. No, both of them are uppercase, meaning that this is an element and this is an element. So this is 1, this is another one, atomicity is equal to 2. HCl, 1 H, 1 hydrogen, plus 1 chlorine, so atomicity is 2. NH3, we did this, 1 nitrogen, 3 hydrogens, so atomicity is equal to 4. CH4, just count, 1 carbon and 4 hydrogens, so atomicity is 5. CO2, 1 carbon, 2 oxygens, atomicity is equal to 3. Section 3, we will talk about mixtures, elements, and compounds in terms of operational definitions and conceptual definitions. What do they mean? Operational definition, when you're talking about something or you're defining something practically, how do you see it practically? Okay. Conceptual definition, meaning when you talk or define something theoretically. Theoretically, how do they look like? What do they consist of? That's conceptual definition. So, first let's talk about pure substances. Pure substances, in terms of operational definitions, they are substances in which you cannot separate it into its components by physical means. What does that mean? For example, if we have water alone with nothing else inside or dissolved with it, it's a pure substance. Can you change this pure substance, this water, into hydrogen alone and oxygen alone physically? No. Meaning what? Physical changes, meaning when you're changing, for example, their state. If you boil water more, will it change into hydrogen alone and oxygen alone? No, it does not happen. So this is its operational definitions. On the other hand, conceptual definitions of pure substances, meaning theoretically, how do you see it? It's a pure substance is a substance in which it contains only one kind of particle. Let's say we have a glass of water alone, meaning pure substance. You will see that it consists of water molecules alone, okay? Because we have only one type of particle or one type of compound, so H2O, nothing else inside, we can define this glass of water as a pure substance. In general, a pure substance is a material usually identified operationally by determining its physical properties. Let's say we have two different substances, two different glasses of liquids. Both of them have liquid inside with no color. How can I determine which one of them, for example, is water? By using their physical changes. What does that mean? Their physical constants. Melting point, boiling point, density. All of these should be constant. For water, you know the melting point is 0 Celsius, boiling point is 100 Celsius, density is 1 gram per cubic decimeters. You can just test it. So for container or glass number 1 and for glass number 2, boil it and see how much is the boiling point. If which one of them is 100, that's water. Freeze it, then melt it. Which one of them has a melting point of 0 Celsius? That's water. Calculate the density. Density is mass over volume. Which one of them has a density of 1? That's water. Easy. Another constant which is considered as a physical constant, it's index of refraction, in which it's not talked about that much in this book. But know that it is also constant. So all of these are physical constants. What do they help us do? To distinguish between two different substances, to see which one of them is which, or which one of them is a pure substance. Let's say we have a glass of water alone, and we have a glass of water in which we dissolved salt inside. So look, this glass of water, which is a pure substance, this is not pure because we have dissolved something inside. The melting point of the pure substance would be 0. Boiling point would be 100. For this not pure substance, the one with salt, the melting point would be lower than 0 Celsius, and the boiling point will be higher than 100 Celsius. So by comparing them, you will know which one of them is pure. We have two types of pure substances. It can either be an element or a compound. So no mixtures are not considered as pure substances because they have more than one thing inside. So the conceptual definition of a compound, and this is, it's a pure substance that has only one type of molecule containing more than one type of atom. So it's a compound. H2, it's a compound. Why? Because in this molecule of water, let's say, we have two different elements. If I say hydrogen, this is a molecule, yes, but it's an element because we only have one element inside, one type of atom. So this is a compound because we have more than one type of atom. So that's the conceptual definition of compounds. Some substances, some compounds, they do not have molecules. Instead, they have ions. So what's the difference, let's say, between H2O water? It has molecules, and NaCl, it has ions. Here you should go back to grade 9. So look, here we have two elements, and here we also have two elements. But what's the difference between them? Here in H2, both of them are non-metals. In NaCl, one of them is a metal, one of them is a non-metal. So whenever we have two non-metals, the compound will have molecules. Whenever we have metal and a non-metal, the compound will have ions. Here we will have sodium, positively charged ion, and chlorine with negatively charged ion. But both of them, H2O and NaCl, both of them are considered being compounds because both of them have more than one type of element. So the operational definition of a compound, meaning practically when you do it in the lab, how would you see or how would you define compounds? A compound is a pure substance that can be separated into different substances or simpler substances by chemical means. What does that mean? Elements, we said we cannot change them into more than one element or more than one thing, more than one substance. Here, a compound, H2O. Physically, you cannot change it. Yes, we agree. But chemically, if you do electrolysis, So by chemical reactions, H2O will be changed into hydrogen gas and oxygen gas. So look, we have changed this substance, which is a compound, into more than one substance, more than one element. So H2 is considered as being a compound. But for example, H2, hydrogen gas, can you change this even chemically into more than one thing, into, let's say, hydrogen and oxygen? No, because it only has one type of element or one type of atom, so you cannot change it. Next, the conceptual definition of an element, which is a pure substance that has only one type of atom, as we have discussed this. The operational definition, you cannot separate it, as we have discussed this too. You cannot separate it by chemical or physical means, both of them. You cannot change it into more than one thing. So that's it for compounds and elements. Next, we have mixtures. Mixtures, we have two types. Okay, we have homogeneous and we have heterogeneous mixtures. Okay, so two types. What's the difference between them? Homogeneous mixtures are all parts are the same. Heterogeneous, all parts are not the same. Meaning, homogeneous, they're uniformly, the particles are uniformly distributed. But for heterogeneous, they're not distributed uniformly. For example, for homogeneous mixtures, salt in water or sugar in water or anything that dissolves in something else. So when you dissolve salt in water, it will disappear, right? And the particles of salt, Na and Cl, they will go and spread out in the entire container uniformly. What does that mean? If I take a sample of this solution from here and another sample from here and another one from here, look, all parts are the same thing. All of them will have the same amount of, let's say, saltiness. But for heterogeneous substances, we have example, sand in water. Sand does not dissolve in water, right? So when you try to mix it, you will have clumps or bits of sand at the bottom of the container because it does not dissolve. So look, if I take a sample from here, another one from here, another one from here, all of them are not the same thing. So they are not distributed uniformly. Something about mixtures is that you can separate them. For example, salt in water. Can you separate salt alone and water alone? Yes, by using, let's say, distillation. Or we can use crystallization. Look, we can use methods to separate them. But for example, for water, you cannot do that. So you can only use chemical methods to separate it into hydrogen and oxygen. So that's for compounds. For mixtures, it's easier. For heterogeneous, because this does not dissolve in water, so sand does not dissolve in water, what do you use? Filtration. And you can easily separate sand from water. So can we consider mixtures as pure substances? No. So the only two pure substances we have, they're elements and compounds. Mixtures, both of them, homogeneous and heterogeneous, are not considered as being pure substances because they consist of more than one thing mixed into each other. Section 4, we'll talk about chemical representations, chemical formulas, how to represent compounds instead of writing down their names. in which we use symbols. As you know, in the periodic table we have more than 100 elements, and each one of them we have many squares in the periodic table. Each square consists of an element in which it has its symbol. So for example, hydrogen is capital H, helium is HE, silicon is SI, and so you all already know this. We have chemical formulas. What do you mean by chemical formulas? Let's say, for example, water, we write down H2O. This is the chemical formula of water. What does it give us? It gives us, or it tells us, the number and the kind of atom in each one of them. What does that mean? For example, here it means we have hydrogen, we have oxygen, so the type of atom. And look, 2 hydrogen atoms and only 1 oxygen, so the numbers as well. And also the ratio is 2 to 1. So for 2 hydrogen atoms we have 1 oxygen atom bonded to it. Generally it tells us the type of element, number 2 number of atoms, and number 3 the ratio. Sometimes if this ratio changes, what does that mean? What will happen to the compound? Will it change or not? The difference between H2O and H2O2. We take this example a lot. So here the ratio is 2 hydrogen to 1 oxygen. Here the ratio is 2 hydrogen to 2 oxygens. Because the ratio is not the same thing, even though they have the same type of element, hydrogen and oxygen, these are not the same substances. Okay, these cannot be considered as the same substances. Why? Because the number of atoms, the ratios are not the same thing, even though the elements are the same thing. So if I say, example, if I say 2H2O, what does that mean? This big 2 right beside H2O, right beside the chemical formula, this is the number of molecules. So it means that we have 2 H2s, just like this. But here, this 2 belongs to hydrogen, and this nothing belongs to oxygen. So the small numbers are the number of atoms of each one of them. Okay? So the big thing is molecule, the small things are number of atoms, small lowercase numbers. You cannot say H4O2. No, we have 2 molecules of H2 separately, not bonded together. But in each one of them, hydrogen is bonded to oxygen. So we have oxygen and 2 hydrogen bonded to it. Next, we have molecular formula. Molecular formula is only specific for molecular compounds. We already talked about this when we have 2 nonmetals bonded together by a covalent bond, so it has molecules, so its formula will be considered as molecular formula, such as H2, such as NO2, such as NO, such as C2H4, 2 nonmetals. Sugar is another compound with a molecular formula, C6H12O6, C12H22O11. All of these are compounds with molecular formulas because they have molecules. But ionic compounds such as NaCl, so a metal plus a non-metal, they do not have molecules, they have ions instead. So they have ionic formula instead of molecular formula. Simplest formula, it's easy, or we call it the empirical formula, which gives us the smallest or the simplest ratios of atoms. So let's say we have C6H12O6. How would I change this? This is the molecular formula. How would I change this or convert this into empirical formula or simplest formula? You just find the common factor between these numbers and divide all of them by that number. So the common number is 6. You can divide all of them by 6. Yes, divided by 6. You will get CH2O. So this is the the empirical formula. The empirical formula does not give us a lot of information. It only gives us the simplest type of ratios in between elements. Another example, N2O4, just divided by 2. So NO2. But if I say NaCl, it's 1, 1, nothing. So this is the empirical formula. If I have NO2, can you divide them? This 1 and 2 divided by anything? No. So this is itself is empirical formula. Do not change it. Let's take an example. Glucose, a sugar found in most fruits, has a chemical formula. What is its molecular formula? This is its molecular formula because it has molecules. All of them are non-metals. Simplest formula, just divided by 6. So CH2O. Potassium chloride, which is an ionic salt, is usually taken instead of table salt by people with high blood pressure. Has a chemical of KCl. What is its molecular formula? Because we have a metal and non-metal, it's an ionic compound. The question is saying it's an ionic compound. Even if you do not know it's an ionic compound, the question is giving you that information. So it's an ionic compound, does not have a molecular formula. Simplest formula, do not change it because you cannot divide it by anything. So KCl, it is its simplest formula. It's a bit tricky, but you have to think before you answer. Basic question 3, give the simplest formula of the following. C6H6 divided by 6, so CH. Ethane C2H6 divided by 2, so CH3. Sodium nitrate, nothing, so NaNO3. SiO2, nothing, so SiO2. Look at this. Let's do the last one, then come back. This divided by 6, so CH2O. Look at this one. If you have a look, you will see that you cannot divide it by anything, right? But look, what would we do? We have CH3COOH. Look, here we have one carbon, we have another carbon, so basically it's C2. We have 3 hydrogens with another one, so 4 hydrogens and 2 oxygens. Then you change it into simplest formula by dividing it by 2. So CH2O. You have to be careful. Next we have how to name binary compounds. Binary meaning we have bi, meaning we have 2 different elements combined together. We call them binary. How would you name them if they are molecular compounds? You have to use this table. We already took this in grade 9. You have to mention numbers, mono. The only tricky thing is that whenever you have mono at the beginning, do not mention it. So the number first, then the name, number first, then the name. Let's take an example. For example, let's say we have NO2. Look, number first, then the name of the element, number first, then the name of the element. Okay, the first element, do not change its name. The second element, you do change it. So number first 2 is di nitrogen, it's nitrogen, do not change it. Look at the second one, mono, you can use mono but not at the beginning. Oxygen, it's oxygen, right? You change it into oxide, so add IDE to it instead of GN, IDE, so oxide. Basic question 4, write the formulas of the following. We have sulfur dioxide, so sulfur meaning it's mono because we do not mention it, dioxide, so SO2. B, phosphorus pentachloride, phosphorus P, penta is 5, chloride is Cl, so PCl5. Dinitrogen, so 2 nitrogen, pentaoxide, pentaoxide, so N2O5. Name the following. This is hydrogen, monoiodide. Here it's carbon, tetrachloride. This is nitrogen, dioxide. Do not forget, do not mention mono at the beginning, even though all of them are one, but we didn't mention it. Next, we have the structure formulas and the atomic models. Structure formulas, it gives us the structure, the bonding between them. It gives us the most amount of information out of all types of formulas between empirical, molecular, chemical. Structure formula gives us a lot. So the extra information in which it gives us, it shows us the bonding between them. So if I tell you it's NH3, you wouldn't know how they're bonded together. But if I give you the structure formula, you know that one nitrogen is bonded to 3 hydrogens. What does it give us? The type of atoms, the number of atoms, and the bonding between them. This is for structure formula. Look at the bonding between them. Sometimes we have the single line, sometimes we have double line, other times we have triple lines. So we have single bond, for example, CC, double bond, 2 lines, and we have even triple bond, but not more than triple. The molecular model, we have 2 different models. We have the ball and stick model, and we have the space filling model. Ball and stick, we use balls to represent atoms, and we use sticks to represent the bonds between them. But space filling, we only have balls in which we represent atoms and we just stick them together. So we do not have any bonding shown, even though they're bonded together. Okay, so for example, hydrogen, the general formula or the molecular formula is H2. Structural, H is bonded to another H. Ball and stick, we have 2 of the same atom bonded together. Space filling, just 2 balls. Same thing goes for H2O and NH3. Do not forget to use different colored balls to represent different elements. The last thing we have is the particle model for liquids and gases, or the difference between the 3 states of matter: solids, liquids, and gases. For solids, as you know, the particles are highly packed, bonded together, highly packed, close to each other. There is no space basically between them. That's why they cannot move that much. For liquids, they're a bit away from each other, so there is space between them. That's why they can move or slide against each other. For gases, as you know, they're free. They move a lot. They do not stop. They are in constant movement. Why? Because there is space between them. For their shape, solids, the shape is constant, does not change. For liquid, it changes. For gas, it also changes. For volume, for solid, it does not change. For liquids, it also does not change. If we have a glass of water of 20 milliliters, we pour it in another shaped glass, you will still have 20 milliliters. It does not change. But for gases, it does change. Okay? And the space between them, basically 0 space or low, not a lot, a bit more. For gases, the most amount of space. Section 3.5. So we'll talk about some calculations. We do some calculations and we will have some rules to follow. First, let's talk about the Avogadro's number and the mole concept. What do you mean by mole? What does it mean when you use it? First, we have an example. If let's say we have 3 different containers. If let's say in the first container we have 32 grams of oxygen gas, the second one 17 grams of ammonia, and the last one 2.02 grams of hydrogen, but their volumes are 22.4 for all of them. So because they have the same volume, it means they have the same number of molecules, which is exactly this much. You have to memorize this number. This is Avogadro's number of molecules. You will use it later on. We have a special rule on how to calculate number of molecules. You will need this number. in which we call it the Avogadro's number. Next, what is a mole? Say for mass, we use grams, right? For volume, we use cubic decimeters or liters or milliliters. For the amount of a substance, we use mole. 1 mole is equal to Avogadro's number again, 23. Okay, so for example, if you have, let's say, 2 moles, you will say 2 times this number. So 1 mole is exactly this much. And instead of writing down this huge number, we just write down 1 mole, for example. Next, we have the atomic mass unit, AMU, okay, which is exactly 1/12 of the atomic mass of carbon-12, which is exactly 12. So 1/12 times 12, 1. So 1 is equal to 1, okay? So 1 AMU is exactly 1/12 the mass of carbon-12, which is exactly 12. You will get 1. Atoms, because they're so tiny, you cannot use other units. We only use AMU, atomic mass unit. For example, if you want to, let's say, change from AMU into grams or from grams into AMU, what is the relationship between them? You have to know that the Avogadro number of AMU is equal to exactly 1 gram. Okay, this is your relationship. You have to memorize it. So let's say if you want to, if the question gives us AMU, you have to change it into grams. Let's say 2 AMU. How would you change it? Write down what you have, 2 AMU times. You have the fraction. What do you have from the relationship? Look, AMU should be right across. So 6.023 powers of 23 AMU here, and 1 gram here, and the final answer should be in grams. If you have grams, you want to change it into AMU. Let's say 2 grams. So 2 grams times, look, the relationship, 1 gram is equal to Avogadro numbers of AMU, and the final answer will be in AMU. So it depends. Just memorize this if you want to change between these two units, AMU and grams. Let's take an example. Given that one atom of carbon-12 has a mass of 12 AMU, find its mass in grams. First, write down the relationship between them. So between AMU and grams, you know that Avogadro number of AMU is equal to 1 gram. So this is your relationship. What do we have from the question? AMU. Write it down. 12 AMU times, you have your fraction. AMU should be right across, so you have Avogadro number, and you have 1 gram above. You will get the answer in grams. Example number 2, convert 1 microgram, which is 1 times 10 to the power of negative 6 grams, into AMU. Here, write down what you have from the question, so you have grams. Write down the relationship. So again, this is your relationship. Write it down. And grams should be right across, so 1 gram. 1.000, it's 1, okay? Do not get confused. And we have Avogadro number, so we have the AMU above. Cross grams, you will get AMU. You can use the calculator. Meaning of the atomic mass. What do you mean by atomic mass? Atomic mass is with no unit, okay? So it gives the relative mass of an atom, of that element, of a specific element, related to or relative to the isotope of carbon-12. So we compare anything that we have. If let's say we have X, we want the atomic mass of this X. What do? You compare it to carbon-12 again, which is an isotope of carbon. The atomic mass or AMU of carbon-12 is 12 AMU. Okay, it's easy. Let's take an example. Example number 3, take fluorine, symbol F, atomic mass is 19. Tell us what is the mass of one atom of fluorine compared to carbon-12, taken as 19 AMU, which is 19 So this is the atomic mass of fluorine. Let us find A, the mass of one atom of fluorine, B, the mass of 1 mole of fluorine. So let's do A first. What do? You get the ratio when we compare it to carbon 12. So you get what you have. So you have fluorine divided by carbon 12. So how much is it for fluorine, the atomic mass, or the mass of one atom? 19/12. Done. First step is done. Get the ratio. Step number 1, ratio of X over carbon 12. So you have 19/12. So how do you get AMU? You know that the atomic mass unit of carbon 12 is 12 AMU, right? So what do? You just multiply it. So you get the ratio, multiply it by 12 AMU, cross it, you will get 19 AMU, which is the atomic mass unit of fluorine. So look, if you have a look at it, even without doing all of these steps, the atomic mass was 19. So how much is it in AMU? It is exactly 19 AMU. So the mass of one atom is 19 AMU. So A, the answer is 19 AMU without even solving it. B, the mass of 1 mole of fluorine atoms. What do? We use conversion factors. How? First, you have 19 AMU, you multiply it by Avogadro number. Step number 1. So now we have the number of atoms, or in AMU, we have units of AMU. You want the mass, because the question is saying, or is asking you to do the mass of 1 mole. So what do? First, convert it into 1 mole. This is exactly 1 mole, because 1 mole is equal to Avogadro number. Then you change this into grams. What units do you have? You have AMU. How do you change AMU into grams? Use the relationship between them. So 1 gram is equal to 6.023 powers of 23 AMU. So write down what you have, multiplied by, we have the fraction, you have AMU here, AMU should be right across, and grams above, cross everything, look, this number, the Avogadro with Avogadro, then 1 times 19, 19 AMU with AMU, so you're left with grams, which is the same exact number. So if you have this question special for the bubble sheet, do not solve it, and we'll just write it down. So we have the atomic mass is 19, so in AMU it's 19 AMU, in mass or in grams 19 grams. That's it. Just like example number 4, the mass of one atom of chromium, find it. That's for A. For B, the mass of 1 mole of chromium atoms, given that the atomic mass of chromium is 52. So the mass of one atom, what does that mean? The unit should be AMU. So the answer is 15 AMU. B, the mass of 1 mole of chromium atoms, meaning it should be in grams. So 15 grams. That's it. So do not get confused with the steps. Just write it down, but be careful with the units. Basic question number 5. This has come a lot in the periodic and final exams. A, what is the mass of an atom of silver? The question should give you the atomic mass of silver. So atomic mass of silver of Ag is equal to 107. So A, what is the mass of an atom of silver in AMU? 107 AMU. What is the mass of Avogadro number of atoms of AMU in grams? 107 grams. What is the mass of 1 mole of silver in grams? 107 grams. That's it. Basic question 6. How many moles and how many atoms are present in if you have the mass of sodium? Before doing this basic question, you have to know some rules. Okay? You can ignore all of this. We have many rules, especially this page 65. We have many rules. It's too confusing for you how they have explained, especially this diagram. I will write them down. here, then you can just write it down on your notebooks. Number 1, we have moles. Number of moles is equal to mass over molar mass. If the question has given you mass, how would you calculate number of moles? You just divide mass by molar mass. And molar mass, now in this page we'll talk about it, how to calculate it. Number 2, number of molecules, number of moles multiplied by Avogadro number. Okay, so N times Avogadro number. For atoms, same thing, moles times Avogadro number, but we have something else, which is atomicity. We already talked about atomicity and how to calculate it. Just count the number of atoms in each molecule. Let's go to this page, then come back to the basic question and solve it. Let's do molecular mass. So the difference between molecular mass, mass of 1 mole, and the molar mass, especially molar mass, is very important. All three of them are the same thing. The way you calculate is the same thing, but they have different units. Okay, so with molecular mass, no unit. With mass of 1 mole, mass, which is grams. Molar mass, in which you'll use this a lot, gram per mole. Okay, so how many grams we have per 1 mole? How do you calculate it? Let's say we have oxygen gas. The question will ask you to calculate the molar mass of oxygen gas, and it will give you something like this. We have brackets, O is equal to 16. What does this mean? The atomic mass of oxygen is 16. The question should give it to you from the periodic table. So what would you do? The molar mass would be equal to, how many atoms of oxygen do we have? 2. So 2 times 16, 32. Done. 32 what? Gram per mole. This is the unit of molar mass. If you want molar mass. If you want molecular mass, same thing, still 32, no unit. If you want the mass of 1 mole, still 32, but grams. Okay, let's do another example. So for example, you have NO, nitrogen monoxide. The question will give you the atomic mass of nitrogen, which is 14. Then we have oxygen, which is 16. What would you do? We have 1 nitrogen, 1 oxygen, so just add them together. When you do one element, when you go to the next one, you plus. So we have 14, so 114, 1 times 14 plus 1 times 16, which is equal to 30. If it is molar mass, gram per mole. Another one. If let's say we have NO2, same thing, nitrogen is 14. This is the question I'll give it to you. Do not memorize it. Even if the question does not give it to you, ask you for your teacher. So we have nitrogen, 1 nitrogen, so 114 plus. We have 2 oxygens, so 2 times 16, so 14 plus 32, which is equal to 46 gram per mole. So look, do you see the pattern, how you do it? NH3, the question will give you nitrogen is 14, hydrogen is equal to 1. So nitrogen is 14, 114 plus 3 hydrogens, so 3 times, how much is hydrogen? 1, so 3 times 1. So it's equal to 17 gram per mole. This is how you calculate the molar mass, the molecular mass, and the mass of 1 mole. Especially molar mass, you will use it a lot, especially in all of these calculations. So let's do basic question number 6. So what do you have in basic question number 6? How many moles? Number of moles are unknown. And atoms are unknown. If you have 11.5 grams of sodium, mass is equal to 11.5 grams of which element? Sodium. And it should give you the atomic mass of sodium, which is equal to 23. Now let's do the first one. Number of moles is equal to what? Mass over molar mass. So how much is the mass? 11.5 grams over molar mass of sodium. It's only 1 sodium, nothing else with it, so you do not add it to another number. So 1 times 23, 23 gram per mole. So divided by 23 gram per mole. So look at the units. Cross, number of mole is equal to 0.5 moles of sodium. The first one is done. The second one, number of atoms. Atoms are equal to number of moles times Avogadro number times atomicity. So how much is number of moles? We just calculated number of moles, which was 0.5 times Avogadro number. How much is atomicity? Sodium in nature is just in a sodium. It's only one thing, and it's 1. So multiplied by 1. That's your atomicity. Then you'll have the answer. 3.01 times 10 to the power of 20. 3 atoms. You can ignore all of this. You already know all of this. Just memorize these rules. You'll use them in other chapters as well. This is the base for you for this year. So you have to memorize them. You have to know when to use each one of them. Let's go to example number 1. How many moles? The number of moles are unknown. How many atoms? Number of atoms are unknown as well. Present in m grams, so we have the mass, it's m. So it's a variable. Of an element of an atomic mass or molar mass, which is m. Okay. How would you calculate number of moles? Number of moles is equal to mass over molar mass. How much is mass? It's m. So m grams over how much is the atomic mass over molar mass. That's it. I'll leave it like that. What about number of atoms? Atoms are equal to number of moles times Avogadro number times atomicity. So how many moles do you have? It was m grams over m times Avogadro number times atomicity. So you do not have a lot of solving in this example. You can just ignore it. It's not that important. Let's do example number 2. How many how many moles? So number of moles are unknown. For B, atoms are unknown. What do we have? Mass is 3 grams. Of who? Of which element? Carbon. And we have the atomic mass of carbon. How would you calculate number of moles? Number of moles is equal to mass over molar mass. How much is the mass? 3 grams. How much is the molar mass of carbon? In nature is just carbon, and the atomic mass is 12. So that's your molar mass, gram per mole. So number of moles is equal to 0.25 moles. For B, how many atoms are there? So number of atoms, as you know, number of moles times Avogadro number times atomicity. So number of moles is 0.25 times Avogadro number. Atomicity, carbon in nature is just carbon, just one atom, so the atomicity is 1. You multiply it, you get the answer. That's for example number 2. It uses a lot of methods. You can just ignore it. Use the easiest solution, the one that you're comfortable with. Example number 3. How many moles? So number of moles are unknown. If we have molecules, number of molecules are known. So for A, what do you do? What's the relationship between number of moles and number of molecules? The rule for number of molecules, it says it's equal to number of moles times Avogadro number. So what do we want? We want moles. So we divide it by Avogadro number. How many molecules do we have in the question? We have 3 times 10 to the power of 20 over 6.023, which is Avogadro number. Number of moles is equal to 5 times 10 to the power of -4 mole. Some people might say or might ask, some students might ask, why didn't we use number of moles is equal to mass over molar mass? Because we do not have mass to do that. Okay, what else do we have? We have molecules. So because you cannot use this rule, think what do you have? In the question molecules, just write down the rule for the thing that you have. You have this rule, okay? Then you rearrange it. What do you have? You have this number which is constant. We have number of molecules in the questions. What can we calculate? Number of moles. You just divide them. What's with it goes as the denominator and the other one as numerator. Then you have your answer. Let's do B. Question B says, what is the mass of the given quantity? So mass is unknown. Now, what do we have so far? Number of moles. Then mass, it's unknown. What is this for? It's for H2O. The question has said that hydrogen is 1, the atomic mass, and oxygen is 16. So, if we have number of moles, we want mass. What's the relationship between them? What rule do we have that has both of them together? Number of moles is mass over molar mass. So can you calculate mass here? Yes, just rearrange it, cross multiply. Mass is equal to number of moles times molar mass. Do we have molar mass? No, but you can calculate it for H2O. So for hydrogen it's 1, but how many do we have? 2. 2 times 1 plus oxygen it's 1. How much is it? 16. So 1 times 16, which is 18 grams per mole. Use that. Okay. So number of moles in the question, the one we calculated in A, 5 times 10 to the power of negative 4 mole times molar mass, it's 18 grams per mole. And the answer should be 9 times 10 to the power of negative 3 grams. It might be a bit confusing at the beginning, but once you have memorized the rules, once you have practiced, it would be easy. Let's do basic questions. Basic question 7. What do we have? For A, how many moles? Number of moles are unknown. How many molecules? Number of molecules are unknown. And atoms are also unknown. Present in 2 grams, so we have the mass 2 grams. Of which element? Oxygen. Oxygen is not O. Do not forget, in nature it's O2. This is very important. If you consider it as just O, everything will be damaged. So let's start. The question should also give you the atomic mass of oxygen, which is 16. Don't worry, the question will give it to you. How can I calculate number of moles? Start with number of moles first. Mass over molar mass. So it's oxygen O2. O is 16, so 2 times 16, 32 grams per mole. This is the molar mass. Okay, so how much is mass? 2 over 32. Number of moles is equal to 0.0625 moles. First one is done. Okay, let's do molecules. Number of molecules, as you know, are equal to number of moles times Avogadro number. So number of moles was 0.0625 times Avogadro number, which is equal to 3.76 times 10 to the power of 22 molecules. Atoms, same thing, you just add atomicities, number of moles, Avogadro number times atomicity. Look, if you consider oxygen being oxygen, the first mistake you will do is, or will be, here. So you'll calculate it as 16, not 32. And you will not get the same number of moles, you will not get the same number of molecules. The other mistake is, if you consider it as just O, atomicity will be 1, right? Which is incorrect. It's O2. How much is atomicity? 2. So be careful. Number of moles, 0.0625. Again, Avogadro number. And atomicity, it's O2. How many oxygens? 2, so atomicity is 2. Multiply everything, you will get the answer. 7.52 to the power of 23 atoms. That's for basic question number 7. Let's do basic question number 8. What do you have from the question? Calculate the mass is unknown, of 1.5 moles, number of moles is equal to 1.5 of calcium atoms. Ca in nature is Ca, and it should give you the atomic mass of calcium, which is 40. So what's the relationship between them? Number of moles is equal to mass over molar mass. Can I calculate mass? Yes, you have everything. So rearrange it, cross multiply. Mass is equal to number of moles times molar mass. Number of moles is equal to 1.5 times how much is molar mass? It's just Ca, just 1. So 1 times 40 is equal to 40. Then you multiply, which is 60 grams. Basic question number 9. What do you have? Calculate the number of molecules are unknown and atoms are also unknown. If we have 1.5 moles, number of moles is equal to 1.5 of which element? F2, fluorine gas, and you will have the atomic mass, which is 19 if you need it. If not, then do not use it. So how do you calculate number of molecules? As you know, molecules are equal to what? Number of moles times Avogadro number. Easy. We have number of moles, they're ready. So 1.5 times Avogadro number, just 9.0345 powers of 23, or 9 times 20 to the power of 23 molecules, if you round it. Atoms, how would you do atoms? Atoms are equal to number of moles times Avogadro again, then times atomicity. Be careful. Again, same thing. Atomicity, what do we have? We have F2. How much is the atomicity? We have 2 atoms, so the atomicity is equal to 2. So times 2. You can just multiply this number by 2, which is 18 times 10 to the power of 23 atoms. Then change it to scientific notation, so 1.8 times 10 to the power of 24 atoms, or just use the calculator, it's up to you. Let's do basic question 10. Basic question 10a. How many moles, number of moles are unknown, molecules again unknown, are present in, if we have 30 grams, meaning the mass is 30 grams of the substance H4CO2, and the question will give you the atomic mass of hydrogen 1, carbon 12, oxygen 16. The question will give you this. How would you calculate it? Number of moles is equal to mass over molar mass. How much is mass? 30 grams over. How much is molar mass? It's H4CO2. Listen carefully. So we have 4 atoms of hydrogen. Hydrogen is 1 here, plus, go to the second one. Carbon, it's 1. How much is it? 12. So 1 times 12, plus, go to the third one. Oxygen, it's 16. How many do we have? 2. 2 times 16. And you will have the answer. So 4 plus 12 plus 32, which is 48 gram per mole. So 30 over 48 gram per mole, 0.625 moles. Moles are done. Molecules, again, number of moles times Avogadro number. So just multiply them, use the calculator. That's it for A. For B, how many moles of atoms do they contain? Meaning the number of atoms, do not get confused. So atoms will be number of moles times Avogadro number times atomicity. So again, 0.625 moles times Avogadro number Look at the atomicity. What did we have? H4CO2. So how many atoms we have? We have 4 hydrogen plus 1 carbon plus 2 oxygens. So the answer is 7. The atomicity is equal to 7. You multiply it by 7. And you'll get your answer in atoms. That's for B. B is also done. Let's go to basic question 11. How many moles, again, molecules, again, are present in, look, we have volume, which is 1120 cubic centimeters. Listen carefully. Of methane, so what do you have? Methane gas at STP. STP, what does this mean? STP means standard temperature and pressure, which is 0 Celsius and 1 atmospheric pressure. At these conditions, we have a rule for volume is equal to number of moles times 22.4. So if we have number of moles, how would you calculate volume? You just multiply it by 22.4. You will get the volume in cubic decimeters. But look at the question. We have the volume in cubic centimeters. First, you have to change it. 1 cubic decimeter is equal to 1000 cubic centimeters. So take this as a rule. Whenever you have something else other than cubic decimeter, you have to change it, then use it, especially in chemistry. So you divide it by 1000 to get cubic decimeters. 1.12 cubic decimeters. Then, can you use this rule? Yes, we can. What do you want? Number of moles, in which it will be volume over 22.4. So volume is 1.12 cubic decimeters. The question over 22.4, you'll get number of moles, 0.05 moles. Let's do basic question 12. The question is saying which one of them has more atoms? 4 grams of calcium or 3 grams of magnesium? You wouldn't know. You have to calculate number of atoms of each one of them, then compare them. So we have basically 2 different elements. Okay, we have 4 grams of calcium and we have 3 grams of magnesium. The question will give you the atomic mass of calcium and the atomic mass of magnesium. For magnesium is 24. So when you want to calculate number of atoms, what do you need? We need moles first. So calculate moles. Number of moles is equal to mass over molar mass. So mass is 4, molar mass is, the molar mass is 40. So 4 grams over 40 gram per mole, which is 0.1 mole. For magnesium, again, number of moles, mass over molar mass, so 3 over 24, which is equal to 0.125 mole. We are done with number of moles. Then what do? Change it into number of atoms. How do you calculate atoms? Easy. Atoms are equal to moles times Avogadro number times atomicity. Calculate the number of atoms of each one of them separately. So for calcium, number of moles was 0.1. Atomicity for both of them, it's 1. Why? Because it's just calcium, it's just magnesium, which is one element, so atomicity is 1. You just multiply it. Here as well, number of moles is 0.125 times Avogadro number, again times 1 because the atomicity is 1. Here the answer will be 0.6023 powers of 23, and here the answer will be 0.752 times 10 to the power of 23. So which one of them is bigger? This one or this one? This one, right? So magnesium, you'll form a sentence. Magnesium, or to be specific, 3 grams of magnesium has more atoms than 4 grams of calcium. Okay, it's not that hard. You just have 2. You just have to organize your stuff. Basic question 13a. What do we have? A compound which has a molar mass of 78 gram per mole. Its simplest formula is CH, so the molar mass is 78. But its simplest formula is CH, so we do not what is its molecular formula, but we know the molar mass of its molecular formula, which is 78. Find the molecular formula. How would you find molecular formula? It's easy. Just calculate the molar mass of the simplest formula. The question will give you carbon is 12, hydrogen it's 1. So what do? Calculate molar mass, which is 12 plus 1, because it's 1, 1. So it's equal to 13 gram per mole. Then we have 2 molar masses. You just divide them. So when you divide them, you will get the ratio or get the number of moles. So N is equal to 78 over 13, which is equal to 6. Now you have the ratio. Get the simplest formula, which is CH. Multiply everything by this ratio or this number, which is 6. So you will get the molecular mass of C6H6. This is its molecular. Basic question 13b. What do we have? A compound of hydrogen. We have hydrogen. We have chlorine and we have carbon. Has its simplest formula of CClH2. This is the simplest formula. If in one of its molecules there are 2 carbon atoms, find the molecular mass. It's easy. If we have 2 carbons here, we have 1, right? What about if we have 2? So you just multiply everything by 2. Okay, so it will be C2Cl2H4. But the question is saying I want the molar mass. The question should also give you the atomic masses of each one of them. So can you calculate the molar mass? Yes, it's easy. So here we have 2 carbons, so 2 times how much is carbon? 12, 2 times 12. Plus we have 2 chlorine, 2 times how much is chlorine? 35.5. Plus we have 4 hydrogens, so 4 times how much is hydrogen? 1. And you will get your answer, 99 gram per mole. Let's do the last one and we're done for this section. Basic question 14. Find the mass of carbon alone, not the whole thing, present, and if you have the mass of the whole thing, C2H5OH or ethanol. How would you do that? It's easy. It's just one rule or 2. You have to follow them. First, we have the mass. Change this mass of ethanol into number of moles. Number of moles is mass over molar mass. How much is mass? 0.92 grams per. The molar mass of C2H5OH, can you find it if you have the atomic masses of each one of them? Yes. So let's find it. The molar mass of ethanol. It's 2 carbon, so 2 times, how much is carbon? 12, plus 5 hydrogens, so 5 times, how much is hydrogen? 1, plus 1 oxygen, so 1 times 16, plus another hydrogen, which is 1 times 1. And the answer should be 46 gram per mole. Then go back, 0.92 over 46 gram per mole. The number of moles will be equal to 0.02 moles of who or which compound? C2H5OH, ethanol. Then what would you do? You'll take this number of moles and bring it here, 0.02 moles of C2H5OH. And listen carefully because we have 2 conversion factors. So look, in this whole thing, how many carbons do we have? 2, meaning we have 2 moles of carbon. Per each molecule or each mole of this whole thing. Okay, how many carbons do you have in each compound or in the whole thing? That's the first conversion factor times another conversion factor. What would you do? Change this number of moles into mass, because we need the mass of carbon. What would you use? You will use the atomic mass of carbon, which is 12. So mole here, look, per 1 mole or each mole of carbon, how much is the atomic mass? 12. So 12 grams of carbon. Then just do your thing. Cross it, cross it, cross it, cross it, and you will end up with mass. Multiply this number by 2, then multiply it by 12, you'll get 0.48 grams. The last thing we have for this chapter, which is section 3.7, we only have one thing, which is Avogadro's hypothesis, again saying that if we have two different gases within the same conditions of temperature and pressure, if they have the same volume, then they have the same number of molecules. So we have this rule. We have two gases, we should have two gases. So molar mass of gas number 1 divided by molar mass of gas number 2 is equal to mass of this gas of gas number 1 divided by mass of gas number 2. Let's do some calculations. Example number 1, it does not need a lot of thinking. It just needs you to assemble the relationship between them. So molar mass 1 over molar mass 2 is equal to mass 1 over mass 2. But let us go to the example number 2. Look at the example. At the same conditions of temperature and pressure, whenever you see this, and both of them have the same volume, so 1, meaning you have this rule to follow. We have sulfur dioxide, SO2, which has a mass of 3.2, and gas G, which is unknown, we do not know what gas it is. It has a mass of 1.4. What is the ratio of the molar mass of gas G? So the unknown gas G, the molar mass, how much is it? What do? Just write down what you have. So gas number 1, SO2. Gas number 2, which is gas G. Mass 1, write it down. Mass 2, write it down. Can you calculate the molar mass of SO2 if you have the atomic masses of each one of them? Yes, just do it here. So we have SO2, if S is 32 and O is 16. So 32 times 1, because we have 1 S, plus 2 times 16, which will be 64 grams per mole. Can you calculate the molar mass of gas G? It's unknown, we do not know the formula, so no. But write down the rule, write down what you have. So M1, molar mass 1 is 64, molar mass 2 it's unknown, mass 1 is 3.2, mass 2 is 1.4, and cross multiply, you get your answer in gram per mole, which is the molar mass of this unknown gas. Let's go to basic questions. Basic question number 15. What do we have? At the same conditions of temperature and pressure, in 1 cubic decimeter of a gas, we have a gas that's unknown, has a mass of, so M1 is 1.5 grams, while the same volume of gas T, another gas which is named as gas T, has the mass, which is M2, of 1.4 grams. Find the ratio of the molar gases of the two gases. So what do? Again, because they're under the same conditions of temperature and pressure, they have the same volume, 1 cubic decimeter. Use this rule. So molar mass 1, molar mass 2. Mass 1, mass 2. You have two things. Can you calculate the molar mass of each one of them? No, they're unknown. And the other thing is that the question itself is asking you to calculate the ratio. It means leave it as a fraction. So M1 over M2, just substitute M1, which is mass 1 and mass 2. Mass 1 was 1.5 grams, mass 2 was 1.4 grams. That's it. Done. This is the ratio of the two molar masses. Let's go to basic question number 16. I have done it already because I've already recorded this video, but the sound was not working that well, so I remade it all over again. Yep. So basic question number 16, again under the same conditions of temperature and pressure. Here we have 5 cubic decimeters of a gas, C2H2. So write it down, but we have 5 cubic decimeters, be careful. M, or the mass, is 15 grams, M1. While 1 cubic decimeter, not 5, we have 1 of a gas D, the mass is 1.4. So what do? Can you calculate the molar mass of C2H2? Yes. Calculate it. It will be equal to 26. The question will give you the atomic masses of carbon and hydrogen. For molar mass to gas D, it's unknown. Can you calculate it? No. But before doing all of this and cross multiplying and the easy part, think. One of them is 5 cubic decimeters, the other one is only 1 cubic decimeter, so the volume are not equal. You cannot use this unless you do something, which is make this one 5. How? Multiply it by 5. But if you multiply the volume by 5, you're not using volume in this formula, right? It doesn't work. So what do you multiply? You multiply the mass by 5. So it was 1.4. You multiply it by 5, okay? Not the one with 5 cubic decimeters, the other one, the one with 1 cubic decimeter. To make them equal, just multiply it by 5. And cross multiply, use this rule. The last thing, which is basic question number 17, again, we have C2H2, which was measured at temperature and pressure. The weight of the mass of the gas was determined to be 1.50 grams. So mass 1 is 1.50. Then we added another gas, which is nitrogen. Nitrogen in nature, it's N2. It's not N, it's N2, do not forget. The mass, it's unknown. So find the mass of the nitrogen gas, it's unknown. Can you calculate the molar masses of each one of them? Yes, if you have the atomic masses here in the question. So for C2H2, again, just like basic question number 6, it's 26 gram per mole. For nitrogen, again, it's N2, so 2 times 14, 28 gram per mole. And use this rule, molar mass 1, molar mass 2, mass 1, mass 2. Then cross multiply, you will get mass 2. In general, the calculations that we had, or the rules that we used in this chapter, which is chapter 3, were all of these rules. So number 1, let's go to number of moles. If we want to calculate number of moles, we have the mass, so how many grams you have in the question. Can we calculate number of moles? Yes, we just divide mass by molar mass. So the mass is how many grams we have, molar mass is gram per mole, the one you calculate, okay? Number 2, number of molecules, we need number of moles, then multiplied by Avogadro number, okay? This number, which is Avogadro number, you have to memorize it. Most of the time the question will give it to you, but it's constant. Okay, so you multiply number of moles, you multiply it by Avogadro, you get number of molecules. Sometimes the question gives you the mass, then it asks you for number of molecules. First you have to calculate moles, then bring it here, then calculate number of molecules. Number of atoms, they are the same thing, number of moles times Avogadro number, but something else is here, which is atomicity. Count how many atoms we have for each one of them, or each element in the molecule. Later in another video, I will explain the difference between atomicity and how to calculate it, and molar mass, how to calculate both of them. So number 4, volume, if, only if we have standard temperature and pressure, okay? It will either give you this STP, standard temperature and pressure, or it will say standard temperature and pressure, or it will give you the temperature, which is 0 Celsius, pressure is 1 atmospheric pressure, so it's standard temperature and pressure. What do you use? You use this rule. Volume is number of moles times 22.4. So get number of moles multiplied by 22.4, which is constant. You get volume in cubic decimeters. Another thing, whenever you have in the question, we have, let's say, cubic centimeters, you have to change it into cubic decimeters divided by 1000, then use this rule. So the units, they're constant. The last thing is when the question says we have 2 gases under the same conditions of temperature and pressure, or we just have two gases, we have their masses, and the volume should be equal. What do? We say molar mass 1 over molar mass 2 is equal to mass 1 over mass 2. Just write them down. So this is gas 1, write it down, gas 2, write it down, their names. Mass 1, write it down, molar mass 1, you calculate if it is possible. Mass 2, write it down, molar mass 2, you calculate if it is possible. If not, it should be unknown, so you cross multiply and you calculate it. Some students get confused between the molar mass and the atomicity. What's the difference between them? How do you calculate each one of them? And when do you need each one of them? Molar mass, you need it to calculate number of moles, because you know number of moles is equal to mass over molar mass. So you need it to calculate number of moles. For atomicity, you need it to calculate the number of atoms. Okay, for molar mass, you need the atomic masses of each element in order to calculate. For atomicity, you do not need the number of atoms. Let's take some examples. For example, we have CO2. The molar mass of CO2, how would you calculate it? Because we have the atomic masses, it's easy. So carbon, how much is it? It's 1. So 1 times, how much is carbon? 12. 1 times 12. When you go to the next element, what do? Plus oxygen, it's 2. So 2 times, how much is oxygen? Oxygen is 16. So 2 times 16. We have 12 plus 32. It will be 44. And the unit is gram per mole. If we have CO2 and we want the atomicity, in atomicity we just count the number of atoms that we have. So these subscripts, the small numbers, you add them. So we have 1 carbon, so 1 plus 2 oxygens, so 2. So the atomicity is 3. Then you use this to calculate the number of atoms. Let's go to the second example of H2SO4. How would you calculate the molar mass of H2SO4? How many hydrogens do we have? 2. So 2 times, how much is hydrogen? Here, it's 1. So 2 times 1 plus, how many sulfurs do we have? 1. 1 times, how much is sulfur? 32. Plus, how many oxygens? 4. How much is oxygen? 16. Then you calculate. So you have 2 plus 32 plus 64, which is equal to 98 gram per mole. For atomicity, again, just count. How many hydrogens? 2 plus sulfur, 1 plus oxygen, 4, which is equal to 7. Another example, the last example, we have MgNO3 by 2. Look, we have brackets. What does this mean? It means that this 2 belongs to oxygen and nitrogen, but not magnesium. So we only have 1 magnesium. So 1 times, how much is magnesium? 24 times 24 plus, look, here 2 times 1, 2. So how many nitrogens do we have? 2 nitrogens. How much is nitrogen? The question should give it to you, which is 14 plus 2 times 3, 6. So we have 6 oxygens. 6. How much is oxygen? 16. So we have 24 plus 28 plus 96, which is equal to 148 gram per mole. So look, you just have to be careful with the bracket. This number belongs to both of them. Multiply them. Then you know how many atoms we have. You just multiply it by the atomic mass of each one of them. Okay? For atomicity here, again, this number only belongs to these 2. So this one, it's only 1 magnesium plus, how many nitrogens? 2 times 1, 2. How many oxygens? 2 times 3, 6. So the answer is 9. Atomicity is equal to 9. Hopefully you have got the difference between atomicity and molar mass, because it's very important, especially molar mass. You use it a lot throughout this course in grade 10, even in grade 11 and 12 you will need it. So make sure to understand it. If not, repeat this video more than once in order to understand.